To create the most detailed images of distant exoplanets and other space objects, a shattered mirror may work better than one that's intact. We'll piece it together for you this week on Light Matters. This is Light Matters for February 11th, 2015. I'm James Lowe.
And I'm Justine Murphy. This week, we're exploring a project that brings together two cutting-edge concepts in optics to pave the way toward a third-generation space telescope.
Now in the early conceptual stages, the Orbiting Rainbows project envisions a telescope that isn't monolithic or confined to one structure like the Hubble. Space telescopes of this nature have to be assembled on Earth and then blasted into orbit.
That's the plan for the James Webb Space Telescope, slated for launch in 2018. But launching anything much larger than the JWST, whose primary aperture is 6.5 meters in diameter, wouldn't be cost-effective or practical.
Orbiting Rainbows would be made up of several smaller components spread over a much larger area. Dr. Marco Quadrelli of NASA's Jet Propulsion Laboratory in California describes the fundamentals of this exotic system.
We're talking focal lengths of the order of half a kilometer and apertures of the order of tens of meters, and a lot of adaptive optics involved. Now, when you have all this separation of spacecraft, you need a lot of intelligence. You need to be able to embed, high-performance computing, feedback loops, and because the whole thing has to operate for decades in an autonomous manner, so without supervision. You have a figure corrector, you have a focal plane. In the formation flying inception of this telescope, all these optical elements are free flyers, and JPL, we have been working on this type of formation flying telescopes for many years.
Such a large aperture could be powerful enough to resolve clouds and continents on exoplanets many light years away, and to collect spectral data about their atmospheres. But those involved with the project say it will be at least 20 or 30 years before the technology is advanced enough.
The primary aperture for this telescope wouldn't be a single mirror, but rather millions of microscopic reflective particles.
That's where the project gets its name. The particle cloud in space would interact with light in much the same way water droplets in the atmosphere form rainbows.
The particles could be shaped into a single cluster or multiple smaller groups depending on the imaging mission. But controlling these particles and extracting useful images from them are sure to be major challenges.
Deconvolution, or computational imaging, has been used for decades to clean up images from imperfect optics. It's what allowed NASA to collect breathtaking images of the cosmos even after the Hubble telescope's main mirror was found to be defective. More recently, similar techniques have been applied to aid imaging through light-scattering biological tissue.
Now, researchers from the Rochester Institute of Technology in New York are working on applying these concepts to the microreflectors that would be used in orbiting rainbows. Professor Dr. Grover Swartzlander explains their progress so far reconstructing an image of 2 points of light using computer algorithms.
So far, we've been able to demonstrate that a bunch of small, randomly oriented reflectors can indeed be used to form a very good image. And we've demonstrated that in the lab essentially by just using glitter from a craft store like Michael's, oriented on a concave surface, and they're kind of randomly placed on the surface. And each image looks very bad, but when you bring about 20 of these images together and use these deconvolution schemes, out pops a very good image of, for example, a binary star system.
To find out more about computational imaging and adaptive optics, we spoke to Dr. Joseph Mate, Chief Scientist at the Army Research Center in Maryland.
You can think of the glitter as a mirror that has been shattered into many pieces, some of which I have lost. But if I know how I've shattered it, and I can characterize how that then performs, I can compensate for it.
Mate is not involved in the Orbiting Rainbows project, but says it would require signal processing as well as feedback mechanisms in order to work. In other words, a computer would need to reconstruct the image while directing the optical components how to move in order to maintain a sharp image over time.
Continually controlling the positions of millions of pieces of orbiting glitter may be an even greater technological hurdle than unscrambling the images they reflect.
Somebody, or the segments themselves, will need to know where all of the other segments are, and and knows that this segment here needs to be moved, and it needs to be tilted, or it needs to be rotated. Those are hard engineering problems that will take a lot of innovation to work out. I think it can be done. I don't want to say, well, that's all that it takes, because maintaining coherence across a kilometer in space is going to be hard.
Swartzlander believes the solution lies in the concept of optical lift.
In theory, the position of each of the hemispherical microreflectors, which he calls optical wings, could be controlled using a uniform light field or a group of precisely targeted lasers.
Just as every airplane wing is designed based on what the functionality would be, so a jet airplane is different than a crop duster, the wing design. The same thing is true for these optical wings, that we need to figure out what is the, an optimal configuration for the shape of that particle to behave the way we want to in the space environment. So we're really at the very beginning stages for that.
So far, Swartzlander and colleagues have been able to manipulate a 20-micron optical wing in water using a near-infrared laser with an output power of less than a watt. In microgravity, even less power would be necessary, though the system would have to counteract some light pressure from the sun.
There's still a lot of work to be done before the Orbiting Rainbows team realizes a system capable of controlling millions of optical wings at once. Swartzlander likens the state of the art to the early days of aerodynamic flight, saying researchers now have only a limited understanding of optical lift and how to exploit it.
And that's it for this week's show.
You can find additional information and resources related to orbiting rainbows, computational imaging, and optical wings at photonics.com/rainbows.
We hope you'll leave us a comment below to let us know what you thought of this week's episode, or to tell us what you'd like to see us do next.
Thanks for watching. We'll see you next week with a special report from Photonics West.